Hi everyone, I'm Dan Fullerton and I'd like to welcome you back to Educator.com. In this lesson we're going to continue our work through the 1998 AP Physics B examination for practice. Starting at multiple choice question number 36, we'll continue through the end of the multiple choice section. So let's dive right in. As I look at number 36 here, we're talking about number of undecayed atoms as a function of time. And what we can see here is if we're looking for the half-life, well, that's the point where the number of undecayed atoms has cut in half. So on the graph, that should be pretty obvious to see that that happens right at point A, which is choice A. Moving on to 37, we're talking about photons of light that have a frequency and momentum. What about the momentum if they have a frequency of 2 times their initial frequency? Well, to do that, let's start by looking at some of the relationships involved. We'll start with our wave equation, v equals f lambda, but just a little bit of math here. We've got 4 times 12, 48 over 3. That's going to be 16 centimeters. So that's the new equilibrium position. So if it starts at the highest point, it falls 16 centimeters to the equilibrium position, and then another 16 centimeters before it stops and will pass back up. Its total must be, how far does it fall? 32 centimeters. And that answer would be choice D. 39. We know an object has a weight W when it's on the surface of the planet at a radius r. So it starts with weight W. What happens to the gravitational force when you quadruple that distance, when it goes from r to 4r? Well, remember, gravity is an inverse square law. If you increase the distance, the force must be going down, and if you quadruple the distance, multiply it by 4, well, it's squared the effect, so that's 16th. So you'll get 1/16 the initial weight. Answer E. Number 40. Trying to find the kinetic energy of a satellite that orbits the Earth in a circular orbit of radius r. Well, if it's moving in a circular orbit, That must be caused by a centripetal force, which is mv squared over capital R. And what's causing that centripetal force? Well, the force of gravity, which is big G times the mass of our satellite and the mass of our planet divided by R squared. So I'm going to solve to get mv squared by itself, multiply both sides by R, and I get that mv squared is going to be equal to G m capital M over capital R. Why did I solve for mv squared? Well, I know kinetic energy is just 1/2 mv squared. So it's going to be 1/2 times, well, mv squared here is just G m capital M over R. So our correct answer there must be choice B. Number 41, we've got a couple objects that are moving parallel to the x-axis, and then they're going to collide, and we're trying to find out a y component of the velocity of one of these objects. Well, first thing I think of when I hear collisions is conservation of momentum. And in this case, we only have to worry about the conservation of momentum in the y direction. We don't have to worry about the x at all, because all we're asked about is the y component of the velocity. So we know that the initial momentum in the y direction must equal the final momentum in the y direction. And since they're both traveling purely horizontally to start the problem, the initial momentum in the y direction must be 0. Therefore, 0 must be equal to, well, the final momentum in the y direction. We have the mass of the 0.2 kilogram object, and it's traveling with the velocity of 1 up. That must be added to the momentum of the second object, which has a mass of 0.1 kilograms and some unknown velocity. So that's a pretty easy equation to solve. 0 equals 0.2 plus 0.1 v, which implies then that 0.1 v equals negative 0.2, or therefore v is going to be equal to negative 2 meters per second, where all that negative means is it's downward. So the correct answer must be A, 2 meters per second downward. 42. We've got a beam of white light incident on a prism, and it talks about what's going on here, producing a spectrum, and as that's filled with air, you get one effect. Then what happens if you fill it in with water, which has an index of refraction of 1.3? Well, you're still going to get a spectrum. You're still going from a lower index to a higher index into the prism, and a higher to a lower index as you leave the prism. But as you have that smaller change in the index of refraction, you're going to get less refraction. You're going to get less dispersion. Therefore, you're going to get a compressed spectrum. It's going to take a lot less space than it did before in order to show all those colors. You're going to get less separation between the red end of the spectrum and the violet end of the spectrum. So our correct answer must be E. 43 and 44 have to do with these distance time graphs. And as I look at these distance time graphs, the first thing I notice is the first graph has a constant slope. That means it must have a constant velocity. Constant velocity for graph 1. Graph 2 has 0 slope, therefore that must have a 0 velocity. Graph 3 has an increasing slope, therefore it must have an increasing velocity. In this case, you have some acceleration. Acceleration does not equal 0. Now let's look at the questions. Talking about the magnitude of the momentum is increasing in which case? Well, the mass isn't increasing, so the only way momentum could increase is if velocity is increasing. That rules out 1 and 2, and the answer must be 3 only. So for answer 43, the correct answer is B. If we go to 44, the sum of the forces is 0. Well, when the sum of the forces is 0, that means the acceleration must be 0 by Newton's second law. The only place where the acceleration is 0, where the acceleration is 0 is 1, constant velocity, and 2, no velocity. So the answer there must be 1 and 2, or answer C. 45. We've got a metal spring inside a uniform magnetic field. We're looking for a condition that won't cause a current to be induced. And if you don't want a current, we can't have any induced EMF. So which of those is going to have some effect where you're not going to have a change in flux? Because remember, the EMF is equal to the opposite of the change in magnetic flux divided by the time interval. So if you were to change the magnitude of the magnetic field, you're going to change the flux. Can't be A. Increase the diameter of the circle. Well, you do that, you're changing the flux. You've got more area. Rotate the spring about a diameter. You're going to change the flux as you rotate that. Moving the spring parallel to the magnetic field. Just moving the whole thing parallel to the magnetic field. Not going to do anything to the flux. I'm thinking D must be our best answer, but let's check. E, moving the spring in and out of the magnetic field. Nope, so you do that, not going to change any flux. So if you want to, you are going to change the flux. So if you want to have no current induced, you can't have any change in flux. Therefore, that must be 45D. All right. Let's take a look at number 46 here. We're looking again for 46 and 47 at a magnetic field on a proton beam. It says, of the following, what's the best estimate of the work done? Well, let's draw a diagram quickly. If there's our magnetic field, and we're going to have protons moving in a circle, let's just draw our circle there. As they do that, the force required for it to move in a circle must be toward the center of the circle. But its velocity is at a right angle to that. And if you recall, work is F delta R cos theta. But in this case, theta equals 90 degrees, so cos theta equals 0. Therefore, the work done must be 0. Answer A. A magnetic field can't do any work on a moving charge. It can change its direction, can accelerate it, but it can't do work on it. 47, what's the best estimate of the speed of the proton as it's moving in that circle? Well, the centripetal force must be caused by the magnetic force, which is QVB sine theta, and that must be equal to m times the acceleration, mv squared over r. Excuse me, because it's moving in a circle. Therefore, we know theta equals 90 degrees, so sine theta equals 1. We could say that QVB equals mv squared over r. Little simplification here. We can divide a velocity out of both sides. Solving for v then, I could say that v equals QBR divided by m. And substituting in my values, Q is 1.6 times 10 to the minus 19. B is going to be 0.1 Tesla. Our radius here, 0.1 meter. And the mass of our proton, about 1.67 times 10 to the minus 27 kilograms. That looks awfully tough, given that you don't have a calculator for the multiple choice part of the question. So let's just estimate the order of magnitude. Right away, let's say 1.6 over 1.67. That's pretty close to 1. Now we've got 10 to the minus 19 times 10 to the minus 2. That's going to be 10 to the minus 21 over 10 to the minus 27. I would say that that's going to be around 10 to the 6th meters per second then, which will give us answer C. And you don't really have anything else that's really close to that value. So you could figure that one out without having to go to the calculator. Checking out number 48 here. We've got a loop of wire in the plane of the page, perpendicular to a magnetic field B out of the page. And it looks like this is a Lenz's law problem, trying to figure out the direction of the induced current in the wire. So, if the magnitude of the magnetic field is decreasing and it's coming out, the induced current wants to create a magnetic field to oppose that, so that it's also going out because that's decreasing. It wants to keep it the same. Right-hand rule is I then wrap the fingers of my right hand around the direction of that induced magnetic field. I'm going to find that this is counterclockwise around the loop, or choice D. A Lenz's law right-hand rule problem. Taking a look at 49, we've got an object making ripples or waves of frequency 20 Hertz, and it tells us the speed. And if the source is moving to the right with some speed, at which of those labeled points will you get a highest possible frequency? Well, a shift in frequency, we're talking about the Doppler effect. And you get the highest shift in frequency when the source and observer are moving toward each other. That must be point C. What you could also see, as you look at the diagram, you can see that C is going to pick up those wave fronts at a higher frequency than the place behind us, behind the point. A would be a lower frequency, for example. But C must be our best answer for the highest frequency. And 50. We've got an object in front of a plane mirror. Well, what do you see when you've got a plane mirror? You see the exact inverse image. So what are you going to have there by the law of reflection? D. All right, number 51. We've got sound waves of some wavelength incident on two slits in a box with non-reflecting walls, and we're going to try and find, well, it tells us the first order maximum, where it is from the central maximum, and we want to find the distance between the slits. All right, it's a double slit diffraction problem. Therefore, d sine theta equals m lambda. And what we're really looking for here is d. So let's solve that for d is equal to m lambda over the sine of theta. But as you look at your diagram there, sine of theta is opposite over hypotenuse. The opposite side is 3 meters. The hypotenuse is 5 meters. So sine theta is 3/5. So as I plug in my values here, I would say that d is equal to, well, m is 1. Our wavelength is 0.12. And sine theta is 3/5. So 3/5 down here, or I can put that 5 up there. 5 times 0.12 is going to be 0.6 over 3, or 0.2 meters. Choice D. 52, another PV diagram, where we've got an ideal gas that corresponds to 0.1 on the graph. What we're looking for is which of the following relationships are true. Well, is T1 less than T3? Well, that can't be the case because it's isothermal, constant temperature. It's not choice A. B, T1 is less than T2. Absolutely, as you go up and to the right, you see higher temperatures. So T2 is greater than T1. That must be our answer, answer B, because T2 is up and to the right, the furthest most up and to the right point on our graph. 53, another ideal gas problem. The absolute temperature of a sample of an ideal gas is doubled, but the volume is held constant. So we know that PV equals nRT. And we want to know what effect that's going to have on the pressure and density. So I'm going to get pressure on a side by itself. Pressure equals nRT over V. And in this problem itself, well, N is constant, R is constant, and V is constant. And what we're going to do is we're going to double the temperature. So if I double the temperature, multiply the right side by 2, I have to double the left side. So we must have twice the pressure. P doubles. How about density? Well, density, remember, is mass divided by volume. Mass isn't changing, and the volume in this problem is constant. That's a given. Therefore, density must be constant in this problem. So the choice where we have double the pressure and density remains the same is choice C. '54. This is just a nasty question. I'm really not sure why they would include something like this on an AP exam, but now that it's here, let's just take a quick look at how you would solve something like this without having any background in it. Trying to find the number of atoms that you could stick on the top of a pinhead, really an order of magnitude estimation problem. Well, the radius of an atom is about 1 angstrom, or 10 to the 10th, 10 to the minus 10 meters, just as a very, very, very rough estimate. Therefore, the area of the atom we'll call pi r squared, which is going to be pi times 10 to the minus 10 squared, or pi times 10 to the minus 20 square meters. Rough, rough, rough. Let's do the same thing for the pinhead. If we want the area of the pinhead, that's going to be pi r squared, which is pi times, well, if the diameter is 1 millimeter, half a millimeter is its radius, so 0.5 times 10 to the minus 3rd meters squared is going to give us, what's that, 25 pi times about 10 to the minus 8 square meters. So if we want the number of atoms, I'll take the area of the pinhead, which is 25 pi times 10 to the minus 8 square meters, divided by one single atom's area, pi times 10 to the minus 20th. And pi's will cancel out. 10 to the minus 8 up here, that'll be 10 to the minus 12 down here. So I get something like 25 divided by 10 to the minus 12, which will be 25 times 10 to the 12th, or about 2.5 times 10 to the 13th, which the closest answer, the only thing even remotely close to that, is choice B, 10 to the 14th. So that's how you could estimate something like this. But if this is the problem that gave you trouble, you're doing just fine. Let's take a look here at 55. In the experiment, we've got light of a particular wavelength incident on a metal surface, and we've got electrons being emitted. Sounds like the photoelectric effect. If we want more electrons per unit time, but we want less kinetic energy with each electron, what should we do? Well, if we want more electrons, that means we need more light waves, more intensity. But we also want them to have less kinetic energy. So if we want less kinetic energy, that means that the light waves that hit them have to have less energy. Those photons have to have less energy. They have to have a lower frequency. And if they have to have a lower frequency, that means they must have a longer wavelength. So the correct answer here would be B. Increase the intensity and the wavelength of the light. Now notice, if you increase the wavelength too much, those photons won't have enough energy to free any photoelectrons. So at a certain point, you keep reducing that wavelength, you're not going to get any emitted photoelectrons. 56. All right, we've got an object moving up and down with an acceleration given as a function of time by A equals A sine omega t, where A and omega are constants. What's the period? Well, period, just right back from simple harmonic motion, is just 2 pi over omega, one of our formulas. So there's our choice right there. All we have to really do is know the formula for 56. 57. We've got a ball at rest that is then kicked. It's given some speed in a direction, and we want to find the impulse imparted to the ball by the foot. Well, impulse is change in momentum, and change in momentum is going to be mass times change in velocity. Our mass is 0.4 kilograms. Our change in velocity from 0 to 5 meters per second is just going to be 5 meters per second, or 2 Newton seconds. Answer C. 58. We've got a wheel with a couple masses on it, and we want to know what the masses are so that it remains in static equilibrium, so that it's not rotating about that center point. That sounds like a net torque equals 0 problem, a rotational equilibrium problem. So if our net torque equals 0, well, our net torque, we've got from the left-hand side, that little m, we've got a torque of mg capital R. From the m on the upper left, that capital M, that torque is going to be capital Mg capital R times the cosine of 60 degrees, and causing the clockwise rotation, so a negative torque. On the right-hand side, we have 2 capital M G R. And again, all of that must be equal to 0. So really what we're doing here is we're solving for little m. This implies then that, let's say, oh, we can do some cancellations here. We've got G and capital R in all of these, so GR, GR, GR. So this implies then that little m plus big M cosine 60 degrees minus 2 capital M equals 0, or little m equals 2 capital M minus capital M cosine 60 degrees. But we know the cosine of 60 degrees is 1/2. So m equals 2 capital M minus capital M over 2, or 3/2 capital M. Answer C. '59. Got a rock thrown horizontally off a building from some height h. We want to know this. Well, the speed of the rock as it leaves the hand horizontally is v0. How much time does it take to travel to the ground? Well, to travel to the ground, we don't care how fast it's going horizontally. That's a vertical kinematic sort of problem. So vertically, we know that the initial velocity in the y direction is 0. We know the change in displacement, the change in distance, the distance traveled, is h, and its acceleration is going to be g, assuming we're calling down the positive y direction. So in order to find the time, I would use the equation delta y equals v naught t plus 1/2 at squared. And since v0 is 0, that term goes away. I can rearrange this to say that t is going to be equal to 2h over g square root, where h was my delta y and a was my g. So the answer there must be E. Now 60, a connected problem, says what's its kinetic energy just before it hits the ground? All right, well, the kinetic energy, we're going to have kinetic energy from its horizontal velocity and its vertical velocity. We could do this by conservation of energy if we wanted to make it really easy. Because its horizontal velocity isn't changing, the contribution horizontally is going to be 1/2 m v naught squared. Now vertically, it initially starts with potential energy mgh, right? Well, when it gets down to the ground, what's its kinetic energy going to be? Well, all that potential has become kinetic. So vertically, that's become mgh. So kinetic energy is the horizontal contribution plus the vertical contribution. And of course, you could go through and solve for the velocity vertically, plug it into 1/2 mv squared, and work through it that way. But the easy way, you have kinetic energy horizontally, and you have this contribution from the vertical component. By conservation of energy, you're all set right there. Answer D. 61, we're looking for which of the statements isn't a correct assumption about ideal gases. Well, molecules are in random motion. Yep, that's one of our assumptions. The volume of the molecules is negligible compared to the volume occupied by the gas, or you've got a lot of free space in there. Yes. The molecules obey Newton's laws of motion. I certainly hope so, yes. The collisions between molecules are inelastic. Absolutely not. We have to assume that all the collisions are elastic. So the correct answer here, the one that is not an assumption that we need to be an ideal gas, is D. 62, another ideal gas problem. Here we have an ideal gas in a tank at constant volume. It's going to absorb heat energy so that its temperature doubles. And we know V1 is its initial average gas molecule speed. V2 is the speed after it absorbs that heat. Let's find the ratio of V2 over V1. So first thing is, let's figure out what happens to the kinetic energy when we double the temperature. We know that the average kinetic energy is 3/2 times Boltzmann's constant times the temperature. So if we double the temperature, we have to double the kinetic energy. So K average is doubling. Well, now we also know kinetic energy is 1/2 mv squared. And if we're looking for velocity, we could rearrange that to say that velocity is 2k over m square root. So what did you actually do if you want to put a 2 in here, if you double the kinetic energy? Well, you've multiplied the right side by square root of 2. You have to multiply the left side by square root of 2. So really, what did we do? We have square root of 2v. Correct answer must be C. All right, moving on to number 63. You've got two people, unequal mass. They're still on ice, they push each other, and they go off in their separate directions. What's true after they've pushed each other? The kinetic energies are equal? No, it doesn't have to be. The speeds of the people are equal? Not necessarily. The momenta of the two people are of equal magnitude. Yes, that's the law of conservation of momentum. C must be correct. Let's take a look at 64. We've got two parallel conducting plates separated by a distance d, and they're connected to a battery of some electromotive force. What's correct if the plate separation is doubled while the battery remains constant? And we're looking for what happens to the electric charge or potential difference or capacitance. Well, let's start. If they're parallel plates, the capacitance is epsilon naught A over D. And if we are doubling the distance, we have to cut the capacitance in half. So we know C is halved. Now, if that's the case, we also know C equals Q over V. Therefore, the charge equals CV. If we cut C in half, what happens to Q if we're holding voltage constant? We must have cut Q in half. We halved the charge. So the correct answer for 64 would be B. The electric charge on the plates is halved. 65, we've got some concentric loops that have different radii, B and 2B, so one has twice the radius of the other. What's the resistance of the wire loop with the bigger radius if the resistance of the one with the initial radius is R? Well, if you double R, and circumference equals 2 pi times R, if you double R, you double the circumference. Therefore, what you're doing is you're doubling the length of your wire. Now, resistance, if you recall, is resistivity times length divided by area. If we've doubled the length, we must have doubled the resistance. Therefore, our answer is D. 66. We've got a uniform magnetic field perpendicular to a plane that's passing through a loop. And we've got two different radii of wires, and the induced EMF in the wire loop of radius B is given. What's the induced EMF if we have twice the radius? Well, remember, EMF is the opposite of the change in magnetic flux divided by time. But as I look at this problem, the changing flux is the same in both loops. As you go from the loop of radius B to the radius of 2B, there's no difference in the amount of flux or in the change of magnetic flux. Therefore, it's going to be the same. Your correct answer is going to be C. There is your induced EMF in the wire loop of radius 2B, the same as you have in the wire of loop radius B. 67. We've got a stationary object exploding into three pieces of different masses. And we know when they explode that we've got a couple pieces moving off at right angles to each other, and it gives us their momentum. We want to find the magnitude and direction of the piece that has the bigger mass. Well, if they started at rest, and you had one piece that went that way, one piece that went that way, by conservation of momentum, your other piece must have gone that way so that their momenta all tally up. So our direction is figured out. Now to get its magnitude, let's use conservation of momentum. In the x direction, we know that the initial momentum, 0, must equal the momentum of the pieces, which is mv to the right plus 3m times our vx prime, the x component of the velocity of our larger piece. Therefore, vx prime must be equal to minus v over 3. And if we did this in the y direction, we're going to get the same math, only to find out that v prime y equals minus v over 3. Could do that by symmetry as well. So what's the total v prime? Well, to do that, we have to realize that our x capacitance in farads times 100 volts squared, or 1/2 times 4, that's going to be 2, times 10 to the minus 6 times 100 squared is 10 to the 4th, so I'm going to get 2 times 10 to the minus 2, and units of energy are joules. Correct answer there? E. All right, so we've gone through the multiple choice portion of the test. Check your answers, see how you did. If there's anything you need to review, go back, take some time, check it out, and then in our next session, we'll start on the free response portion of the test. Thanks so much for your time, everyone, and make it a great day.